Okay, so welcome back to another video. So here we have an indefinite integral, and inside of our integrand we actually have complex values. So we have the integral from 0 to infinity of I to the power I times x to the power n dx. So we have a closed formula that we would actually like to solve for, and we also have our parameters such that n is strictly greater than 0, followed with n is strictly less than 1. I put the union symbol together to put that as a sort of set. So this actually might be interesting as a fact that because I to the power I, as you've seen everywhere on a bunch of references and resources, that it actually does come down to a real number. But what if we actually expand this a little further such that because that the complex value I on its own is actually a periodic function of 2 pi. So let's actually instead expand that out even further with that generality. So with that in mind, if we actually just use that, if we actually use that idea, then we can actually do the substitution, and then yet it actually applies with a u-substitution we're actually going to be using, such that putting the new in the new variable, that it actually comes down to some interesting functions that we'll be utilizing that will actually get us the closed form we want to. So with that out of the way, why don't we actually just jump right in? So let's first start off with I to the power I. So what we know is that just the base I itself, it is a periodic function, but specifically if we actually look at things in terms of the complex plane, it's actually equal to e to the power I times pi divided by 2. And as mentioned, that it's a periodic function that it actually it is equal to I at every single pi over 2 plus 2 pi k, for k is some integer. So we can actually expand this out to say e to the power I, and then multiply by pi divided by 2 plus 2 pi k, and then now close that off, and then that's raised to the exponent for I, and also I'll put in, well, let me actually expand this out first. That if I distribute the I back into here, so it's I squared we know is equal to -1, which is just e then to the power negative, and I'll keep this in parentheses, pi divided by 2 plus 2 pi k, such that k is an integer. So with that out of the way, now let's actually plug in back our substitution. So 0 to infinity of now, plug this back in, so I have e then to the negative pi divided by 2, that's the parentheses over here, and then plus 2 pi k, then close that off, then raise to the power x to the power n, then dx. So if you just apply the same thing again, just move the x to the power n back into here, distribute to that exponent. So now we have 0 to infinity of e to the power negative x to the power n, and then multiply by pi divided by 2 plus 2 pi k, and then finish it off or close that off with dx. All right, so now here comes the u-substitution we're going to be using. So what are we actually going to let u be? We're going to let u be this entire thing excluding the negative. So now with that explained, or rather with that being said, so we're actually going to do now the u-substitution. So why don't we actually let u equals x to the power n, and then multiply with pi divided by 2 plus 2 pi k. So why don't we actually solve for x on its own? So I'll first divide the pi divided by 2 plus 2 pi k to both sides, and then that's just left with equal to x to the power n. Even though this thing is under the denominator on that side, why don't I multiply it 2 for both the numerator and denominator, just so we don't have a rational number underneath the denominator. And then afterwards, that's still equal to x to the power n, and to get rid of that n, we'll just raise that power to 1 divided by n, which just leaves us with x equal to, so 2u divided by pi plus 4 pi k, and then to the power 1 divided by n. So now let's differentiate both sides, so du and dx. So now applying this, so I have that du is, of course, this is just a constant over here, so we actually just take the power rule of this specifically. That's going to be pi divided by 2 plus 2 pi k, and then multiply with n, then times x to the power n minus 1, followed with dx. So of course we want the dx on its own, so there's some things we're going to have to do. For one, that we'll actually have to divide this entire thing over here just to get it by itself. And to make things a little bit better, that's such that makes the simplification a lot easier, why don't I actually write it in this standard form. So first, dx is on its own, and then now after performing the division, what we'll have is this is x, so that's because of the -1. When you do the division, that we're just raising that up back into the numerator, and then that's just left with pi divided by 2 plus 2 pi k, and then times n times x to the power n. Okay, so far that's still in the world of du, then we'll simplify things even further, such that for 1, as with the same reasoning, we'll just multiply 2 to both the numerator and denominator just to get rid of that rational number on the bottom. So now that'll be 2x and then divided by, so this is going to be pi and then plus 4 pi k, then times n to the power, or n times x to the power n, so still du. And then continuing forward, that we have, it's a good thing we solve for x on its own, that we can actually just plug it over here. So now that'll leave us with 2. Then now substitute the x over here. So that means I have 2u divided by pi plus 4 pi k, then divided by, or to the power 1 divided by n. And so now on the bottom, let me rewrite some things. So I have n and then multiply by pi plus 4 pi k, and then x to the power n, which you can just go back to over here, you just divide the pi divided by 2 plus 2 pi k back into both sides, simplify it down, and so the x to the power n can simply just be written as 2 times u, then divided by pi plus 4 pi k. Okay, so du still equal to dx, so let's simplify some things even further. So you'll notice that for 1, that the 2's are actually going to cancel out from here and here. The pi plus 4 pi k is going to cancel from over here. And so now this is just going to be n times u under the denominator. And we can actually now reduce things even further. So let me first write out the what we have established so far. So we have 2u, then divided by pi plus 4 pi k to the power 1 divided by n. And then now this is still being divided by n times u, then du. Then we can actually continue to establish even further that I'll just separate the 1 divided by n, because that's factoring out the n from over here. And then we have a u over here. So if you bring everything into the exponent over here, I can actually also bring that u back into that base as well. So it becomes a 1 divided by n minus 1. So I have 2 to the power 1 divided by n multiplied with u to the power 1 divided by n minus 1, all being divided by pi plus 4 pi k quantity to the power 1 divided by n, then du, which this is still equal to dx. So now with that out of the way, now we can actually go back to the original integral from what we did the substitution. So let me actually change to a different marker for this. So now our new integral, so we have the integral from, so change the bounds, but actually it's still going to remain the same when you actually plug in for x and into the world of u. It's going to be from 0 to infinity. What we have now, this is going to be 1 divided by n. Then now this is going to be e to the power negative u. And then now afterwards, we actually just put in the substitution of our new dx differential in the world of du. So what we have now is this is going to be the following. So I have 2 and then divided by, so I'm also writing things a little simpler as well. So pi plus 4 pi k, then to the power 1 divided by n, multiplied by u to the power 1 divided by n minus 1, and then du. So now we can actually factor some things out since this thing does not depend on u, so that's a constant. Same thing for the 1 divided by n. So I have 1 over n and then multiply with, so 2 divided by pi plus 4 pi k, and then to the power 1 divided by n, then multiply with the integral from 0 to infinity of e to the negative u multiplied by u to the power 1 divided by n, and then minus 1 du. Look at this. This is actually a standard definition of a special function I mentioned. And what is that function? That is indeed going to be the gamma function, which I will write the definition. And there's also a close recurrence relation formula we'll be using. So let me first write that. Gamma of n, so this is also for the real part of n is strictly greater than 0, is going to equal to the integral from 0 to infinity of, so t to the power n minus 1, and then multiply with e to the negative t, then dt. Recurrence relation we'll be using such that for gamma of n plus 1, that's the same thing written as n times gamma of n. Okay, so with this in mind, you'll see that the specific input we had to put in is that this is actually just gamma of 1 divided by n. Okay. Closing things off forward, I have 1 divided by n, and then multiply with gamma of 1 divided by n, then multiply with 2 divided by pi plus 4 pi k, and then to the power 1 divided by n, which of course, this is going to be reduced now using that recurrence relation over here. This is going to be written as 2 to the power pi, or 2 divided by pi plus 4 pi k to the power 1 divided by n, and then multiply with gamma of 1 divided by n plus 1. And if you want to continue simplifying things further with that exponent, this is actually can be written as the same thing as the nth root of 2 divided by pi plus 4 pi k, and then multiply with gamma of 1 plus 1 divided by n. And this is to establish that this is n is greater than 0, strictly greater than 0, and n is strictly less than 1. But now, actually, if you take things a little further, if you notice that, of course, k is inside of our radical, our nth radical, and of course, that being a non-negative function, we actually have to change our parameters up just a bit because we set that k for our parameters, a periodic function, we're dealing with integers. So if you consider the negative values over here, you're actually going to get something of a negative value inside of the square, inside of our radical, which, you know, those numbers don't exist. So we'll actually have to change this up such that it's actually valid specifically for the natural numbers, but also including the number 0. So the natural numbers, and I'll just denote the 0 as a sub-0 back over here, and then k is the natural numbers including the number 0 over here. And so with that being the case, we have our closed form for our imaginary slash, you know, complex integral that's pretty neat if you ask me. So there you have it. All the generalities expanding with, of course, I being a periodic function of, you know, add this with 2 pi k for, now in this case, k is a natural number, including the number 0, and just like that. So yeah, that's pretty cool if you ask me.